Hello, in this video we're going to be starting Chapter 6. In the first part of Chapter 6, we're going to be learning about something called the normal distribution. The normal distribution is something that you might run into whenever you work with continuous random variables. If you remember, a random variable is something that we count or measure in a probability experiment. A continuous random variable would be something that we're measuring, whereas discrete would be something that we're counting. Now, with continuous random variables, the value can take any number in some interval. Well, one of the distributions that you might run into when you work with continuous random variables, it's called the normal distribution. The normal distribution is a very common distribution. It's not the only distribution, but it is one of the most common. So we have a whole chapter dedicated to it. Now, the normal distribution, if you were to look at it as a graph, it would have this kind of bell-shaped curve that we've talked about before. Now that equation would be the mathematical equation for that bell curve. You really don't need to worry about that equation. We're going to work with the normal distribution primarily in terms of its graph, primarily in terms of this bell curve. Now there are some properties associated with this normal distribution. First, it has this bell-shaped curve. That's what really distinguishes it from other distributions. The mean of the distribution is located right in the center. So whatever the mean of the distribution is, you'll find it right in the center of the bell. The standard deviation is going to determine how wide that bell is. So there are two special points on this bell curve that are called inflection points. That's where the curve basically switches from being a upside down U shape to what would be a right side up U shape. Okay, and same thing on the other side, switching from upside down to a right side up U shape. Those inflection points are located one standard deviation above and below the mean. So the bigger the standard deviation, the further out those points are, and the wider the bell shape becomes. The smaller the standard deviation, the closer those inflection points are to the mean, and the narrower the bell shape would be. The bell shape is symmetric around the mean, so if you were to fold this bell shape in half right along that dotted line that runs through the mean, the left and the right-hand sides would match up exactly. The bell curve is continuous. That means there's no breaks in it. It just has this one peak, which is at the mean. And areas under the curve are going to correspond to probabilities. So here's what I mean by that. If you remember with our discrete random variables, when we looked at the graph of them, we had those sticks or those rectangles, and the height of the stick or the height of the rectangle told us the probability for that particular value of x. When we work with continuous random variables, we usually don't ask questions about the probability that the variable is equal to a certain number. We usually ask questions about the variable falling into some range. And if you were to identify that range on a number line and then shade underneath the curve, however much area you have shaded, that would represent your probability. So for example, let's say that we had a normal distribution. So let me draw a bell curve in here. And let's say the mean of that distribution was 75. You might ask the question, what is the probability that the random variable ends up being greater than 80? So rather than saying equal to 80 or something like that, usually with continuous random variables, we're saying what's the probability that the variable is greater than a number, less than a number, or maybe between two numbers. So if we said what's the probability that the variable is greater than 80, we would draw our bell curve and shade everything to the right of 80. And then we would have to figure out how much area we've shaded. And that's what we're going to learn how to do in this chapter. Now, kind of related to this property is that the total area under the bell curve is always equal to 1. Okay, that's a helpful property to keep in mind. Okay, now in the first section of Chapter 6, we're going to look at one special case of the normal distribution called the standard normal distribution. The standard normal distribution is when the mean is equal to 0 and the standard deviation is equal to 1. Okay, so there's a lot of different normal shaped bell curves out there. If you have the one where the mean is equal to 0 and the standard deviation is equal to 1, then you're talking about what's called the standard normal distribution. When we work with this special case, we use a special letter for the random variable. Instead of using x like we usually do, we typically talk about the random variable with the letter z. Okay, so we could have some questions. I've got a lot of them listed here. I'm not going to go over every single one, but I'll go over a few of these with you. For example, we could say, what's the probability that our random variable z is less than 1.62? Well, I'm going to draw my standard normal curve here. I've got 0, which is the mean, right in the center. I've got 1.62 marked in roughly the right place on the right side of the number line there. And since the question says, what's the probability that z is less than 1.62? I'm shading all of this area to the left of 1.62. Less than means left. So when you have the probability that z is less than this number, you shade to the left. Now we have to figure out how much area has been shaded here. Well, we have a chart that's in the back of the book. It's also in the formula card called the Standard Normal Distribution chart. This chart can help you find the amount of area that is to the left of a certain z value. Now, in this case, the z value that we're dealing with is 1.62. So what I'm going to do is I'm going to go to the row where I see 1.6, and then I'm going to go to the column where the second decimal digit is 2. So if you can combine the 1.6 and the 0.02, you get 1.62. Okay, so think of the row here, 1.6, and then the second decimal digit in our z value is 2. So you'll go to the column that has this number where the second decimal digit is 2, and then just take the value from the chart that you see there, 0.9474. That is the amount of area to the left of our z value. That's exactly what we're looking for. So 0.9474 would be our answer. Okay, now, what if we have, let's take this one here. What if we have the probability that z is greater than negative 1.16? Well, I'm going to draw my standard normal bell curve, put 0 in the middle. Question's asking about negative 1.16, so I go ahead and mark that on the left side of 0 since negative numbers are on the left side. Now, when the question says z greater than negative 1.16, I shade to the right. So notice I got all this area shaded to the right of negative 1.16. We're going to have to figure out how much area we've shaded. Now, if we go to our standard normal chart, and this chart has 2 pages to it. There's a page for positive z values and a page for negative z values. Okay, if we go to the row for negative 1.1 and the column where the second decimal digit is 6, the number that we have there is 0.1230. Now, that 0.1230 represents the area to the left of the z value. So that 0.1230 is actually the unshaded area to the left of negative 1.16. Okay, the chart always tells you the area to the left. In order to get the area that I've shaded to the right of that value, what I'm going to do is I'm going to start with the number 1, which represents all of the area under the curve, and then I'm going to subtract the 0.1230. So that's kind of like cutting away that unshaded portion. So what's left over, which is 0.8770, that represents the shaded region. Okay, so anytime that the question says the probability that z is greater than some number, you're going to have to take this kind of strategy here where you draw the picture, shade to the right, look up the z value in the chart, and then remember that's the unshaded portion, so subtract that from 1. Now we might also see questions like this one where it says the probability that z is between 2.00 and 2.47. So if I draw my bell curve and put 0 in the center, I can mark down 2.00 and 2.47 and shade in between. Now, in order to figure out how much area that we have here, what we're going to do is we're going to look up the 2.47 first. We always look up the number that's on the right side of the shaded region first. We're going to figure out how much area we've got to the left of that. So that would give us all of the area to the left of that z-score. Some of that area is shaded, some is not. So then what we'll do is we'll look up the 2.00, and that's going to tell us how much area is to the left of it, which is all the unshaded part. So we'll take that away from the first value that we looked up. Okay, so let's look up 2.47 first. So back to our positive side of the chart here, we're going to look up 2.47. Okay, so here's 2.4, and then the column 7 is all the way out here. So 2.47 is 9932. And while we're at it, let's look up 2.00. So that would be this number here. Okay, in the row we're 2.0, and the first column has a second decimal digit of 0. So 2.00 has an area of 0.9772 to its left. Okay, so we look up the 2.47 first, and we got 0.9932. Now remember, that was this shaded portion plus this unshaded portion. We want to subtract that unshaded portion, which is everything to the left of 2.00, which, if you remember, was the 0.9772. So I subtract those two, and I get 0.0160 for the shaded area here. Okay, and that would represent the probability that our random variable z is between 2 and 2.47. So whenever you're looking for the probability that z is in between two values, look up the value that's on the right side first, get that number from the chart, and then subtract from it whatever you get from the chart when you look up the number on the left side of the shaded area. Okay, now sometimes we want to ask the questions in reverse. So sometimes we want to have a situation like this where we've got some area that's shaded under the standard normal curve, and that area is given to us, and we're trying to find the z-score. So in this case, we've got an area shaded to the left of some z-score that is 0.9798. If we want to find that z-score, what we're going to have to do is we're going to have to go through our chart here, and we're going to have to see if we can find the number 0.9798. Well, there it is. Now, in order to get the z-value, check the row, 2.0, in the column, second decimal digit 5. So our z-score that has this area to its left is 2.05. If you've got an area shaded to the right of your z-score, like we do here, an area to the right that's labeled 0.1788, remember the numbers in the chart represent the areas to the left of the z-score. So before you can go to the chart and start looking for this number, you're going to have to figure out how much area is to the left of the z-score, and then go look for that. So remember, the whole area under the curve is 1. Subtract the 0.1788, and that leaves you with 0.8212 is the unshaded area to the left of this z-score. This is actually the number we're going to have to look for in the chart, because that's the area to the left of the z-score. So let's look for 0.8212 in the chart. Okay, 0.8212. Okay, so we're looking through. By the way, these numbers that are in the chart, if you read them like a book, at least on the positive side, they continually increase. So if you read from left to right and go down, these numbers are continually increasing. So we're looking for 8812. I think that was the number we were looking for. Oh, no, 8212. Okay, so we're looking for 8212, which is right here. Okay, so we're in the row for 0.9, and we're in the column where the second decimal digit is 2, so 0.92 is going to be our z-score that has the area of 0.1788 to its right. Okay, now sometimes you'll run into this situation. This looks just like one of the problems we just did. There's an area shaded to the left of the z-value, and that area is labeled as 0.7259. Okay, let's see if we can go find this area in the chart, 0.7259. Okay, so 0.7259. Well, here's 7257, and then it immediately jumps up to 7291. The number we're looking for is not in the chart. It's actually in between two numbers that are in the chart. So if the number you're looking for is in between two numbers in the chart, what you can do is you can go ahead and mark that down and say, okay, we had 7257 in the chart, 7291. We're looking for a number that's in between, which is 7259. Then see if the number you're looking for is closer to one of these than the other. 7259 is closer to 7257 than it is to 7291. So just take the z-score for the 7257, which that one would be 0.60. Okay, so if the number you're looking for is not in the chart, no big deal. Find the numbers that it's in between, and then take the z-score for the closest value. Okay, now here's another one. Pretty much the same picture, but this time we're looking for the area 0.7719. That's the area to the left of this z value, 0.7719. So let's see if we can find this one. Well, here's 7704 and here's 7734. We're in between those two. Okay, so I mark down the 7704 and the 7734, and I say I'm in between when I'm looking for 7719. I'm checking to see if I'm closer to one of these values than the other. But if you notice, we're exactly halfway in between. Okay, 19 is 15 away from 4. 19 is also 15 away from 34. So you're equidistant to these two numbers. In this case, what you have to do is take your two z-scores and average them. So we're in the row for 0.7, and we're looking at columns 4 and 5. So we have 0.74 and 0.75. We're going to average those z-scores. So we're going to take 0.74 plus 0.75 divided by 2. That gives us 0.745. Z-scores are typically rounded to 2 decimal places, so we'll call that 0.75. Okay, so those are some of the things that we learn in section 6.1. The skills that you learn in this section are essential to be able to do the rest of chapter 6, as well as what we do in the following chapters. So make sure you spend some time, practice this, study this, really try to master this standard normal distribution. Okay, I'll see you in the next video.